too much interest, so I need to give preference to the audience. Okay, so our third speaker is Dr. Nasrin Fatullah-Sadeh Aitar. I don't know how I pronounce that. Nasrin has recently received her PhD in water resources engineering at Urmia University in Iran. During her PhD, Nasrin spent some time actually here at the University of Adelaide, here in Australia, sponsored by the Iranian Ministry of Foreign Affairs. Nasrin is currently a lecturer at Urmia University of Technology, and she's a project manager at Urmia Lake Institute. Her research interest includes data science in water engineering, hydrological data modeling, and data pre-processing to overcome non-stationary time series in hydrological parameters. She's passionate about teaching, and she's running online education programs using our software with students in different parts of the world. So now I'm going to head the stage over to you, Nasrin, to start your talk.
First of all, hi everybody, and thank you for dedicating your time for listening to my presentation. Thank you for your great introduction, Jessica. I know that it's 3 a.m. There in Australia. Thank you for moderating this session. Especially thanks for the let me share my screen. Sorry. Especially thanks for American Society of Civil Engineering and Dr. Maria for giving me this privilege to have my presentation. And I want to start machine learning application, enhancing the prediction accuracy of data-driven models for stream flow based upon nonlinear time series. I want to give you a quick overview of my two recent works, which are published in Applied Sciences Journal and Engineering Application of Computational Fluid Mechanics based on this Urmia Lake Basin. Let me show you, first of all, the study area that I want to talk about to you. This is our planet, and this is Iran. You can see Iran here, and my country. And in the northwestern of Iran, there is a lake here, Urmia Lake. I'm here now. I'm living in Urmia. I was born here in Urmia, and this is our Urmia Lake. I want to talk to you about this lake here and the application of the machine learning techniques that we used. We have 6 main basins in Iran. We can divide these 6 basins of Iran. One of them is Caspian Sea, Persian Gulf, Urmia Lake Basin, Central, Hamun, and Sarax. This is Urmia Lake Basin, which I want to talk about you. Urmia Lake Basin has the total 3% of total area of the country, and it has 5% of renewable water resources in Iran. Let me tell you a story about Urmia Lake. I was born in Urmia, so I have a lot of memories and good memories here. When I was a child, we went there for having fun, for swimming. The whole family is gathered each other, going there, having swimming, using the sludges there for therapy. And so the Urmia Lake is one of the largest hypersaline lakes in the world. First in the Middle East and second in the world. It used to have a lot of tourists, 102 islands and national parks. It's the home of migratory birds such as flamingos, pelicans, ducks, etc. It's the main habitats of brine shrimp Artemia. And in recent years, in the past 2 decades, this Urmia Lake started to shrink. So it shrunk to the tenth of its original area since these past 2 decades, and the lake was sliced in half in 2008 because of creating a breach here. It has some climate change and lack of precipitations are the cause of the shrinking Urmia Lake, damming, persistent general drought, agricultural land use, traditional irrigation systems, pumping groundwater, and unauthorized irrigation wells are the causes of this shrinking. So this shrinking have some effects on human health, on human, our respiratory systems. If the Urmia Lake is going to shrink totally, so it may cause a lot of salty storms. The tourism sector lost out. It decreases the agricultural land productivity. Urmia is an agricultural city. So we have a lot of agricultural lands around the lake. So if the lake shrunk, we decrease the agricultural productivity, and poor air, land, and water quality are these effects of this shrinking. You can see here that Urmia Lake is have the same fate as the Aral Sea, which is located between Kazakhstan and Uzbekistan, and the Salton Sea, which is located in California. So Urmia Lake has been drying up and shrinking for decades. You can see here we have in 1972 the Urmia Lake was in good mood, but after some years, and in 2014, you can see that all the half of the lake are shrunk totally. And Aral Sea has largely dried by 2010s, and Salton Sea entered the Nesodiv in 2018. So this is the last photo of the Urmia Lake, which is in 2020. Because of some restoration programs, the Urmia Lake are going to live again and restore. And in 2016, the National Geographic had a news about a giant green lake turned into blood red. And they found out that because of the salinity increases and warm water high salt concentration, this Urmia and the breeding of Duranilla algae, it goes to blood, and this make this scene like here. This is the photo which we took a couple of weeks ago. This is the white salt crystals, a good scene here, you can see here. And in the past, I remember that we used to use these ferries and go across from Urmia to Tabriz, our neighbor city. This is so in 2008, the government tried to create this bridge, this Urmia Lake Bridge and causeway, 15 kilometers causeway designed to shorten the travel between the cities of Urmia and Tabriz. Okay. Urmia Lake is fed by 13 permanent rivers, you can see here, and the two important rivers which are feeding this Urmia Lake is Zarinerud and Siminerud River. I want to talk you about this application that we used for machine learning techniques for our work. Machine learning is a science that enables computer applications to learn about being explicitly programmed. In principle, machine learning develops model and algorithms can predict an output value with an acceptable error. So we have some input values and then output values from the machine. So time series is another applications of machine learning. They are an ordered set of observations with respect to time periods. Time acts as a reference point in relation to entire procedures. So we use time series, string flow time series for our work. So machine learning processes, you can see here, we have some data sets, then we do data cleaning and feature engineering, training the data, then using the algorithms and training the models, and finally evaluating the models. So why water-related issues are important? Why water-related issues and modeling are important? In this world, the number of diversity of water-related challenges are large. So hydrological modeling can be efficient in order to analyze, understand, and explore solutions for sustainable water management in order to support water managers. And these innovative models and approaches with high accuracy can help decision makers to save money and time and etc. So stream flow is such a nonlinear hydrological variable, and it has a primary role in decision and management of water engineering. So as you know, stream flow has impact on agricultural irrigation demand, drinking water demand, reservoir management, water quality parameters, hydroelectric systems, and extreme hydrological events. So because of this complexity, non-linearity, and non-deterministic, and having a non-stationary behavior, we should consider some other equations and works to understand this better. So modeling with data-driven techniques, recently a lot of scholars, a lot of scientists use data-driven models, which are the main, consisted of the two main groups of artificial intelligence and time series model to model these hydrological variables. But because you know that hydrological parameters have a stochastic nature, so the observed data are not deterministic, they are not implicit. You can't just say this is our equation and it's finished. So we should use some other techniques. We should add some random parts. We should add some stochastic terms to this phenomenon, or some nonlinear time series, to adding some nonlinear equations to these techniques to have good results and accurate output. So modeling with nonlinear techniques, recently nonlinear time series modeling by researchers could be divided into considering the structural asymmetry of models in conditional mean and cortices. Autoregressive conditional heteroscedasticity models, the model is used in economics, finance, and recently in hydrology. So we use this model in order to deal with time series and representing the changes of variance during the time. So using this model as a stochastic part and adding to other deterministic models is our innovation. Another nonlinear techniques that we can use and we implemented in our software that are threshold models in hydrology. You know, threshold is very important in hydrology because for making decision in hydrological fields. For example, if you have a threshold, if the streams are bigger than that threshold, maybe you have some floods or another extreme events. And if we have less than that threshold, maybe we have some droughts. So thresholds are very important for us and we should consider it carefully. Our main goal of this first study, we used GP models with different lags as a deterministic data-driven techniques. And then we analyzed errors by two different nonlinear approaches, namely our CH and SETA models. And at last, we combined them with GP models for our 4 stations. Okay? So in first study, we used eastern part of the Urmia Lake, and we used 4 stations of Daryan, Saidabad, Qırmızıgül, and Lighvan as a selected hydrometric stations, and we used Lighvan Chai, Saidabad Chai, Qambar Chai, and Daryan as rivers. You can see here the annual values of stream flow with their geographical information, and we use 45% of data for calibration and 25% of data for validation stage. So the data lengths that we used are from 1971 into 2010. These are the statistical characteristics of the data in both calibration and validation stage. This is our study flow chart that we, first of all, we collect the historical data, then we divide data after cleaning and cleaning the data. We divided the data into two groups. We transform in the data into normal process, and we use the stationary analysis of the data with two tests of ADF and copy-SS, and then we model the stochastic part with CETAR and RCH models. After that, modeling the deterministic part of the models in different lags, and finally we combine the two parts of the predicted and find out that if the models are improve the models or not. The data preparation in this study are some pre-test pre-modeling tests, which are stationary and nonlinearity. The ADF and copy-SS tests are used for stationarity, and the LR tests used for the finding out the potential for nonlinearity. So with the 95% of confidence level, we found out that all the data are stationary and they have the potential to model as a nonlinear. So these are the autocorrelation and partial autocorrelation of this stream flow. For the CETAR models, we should find out the delay, order, and Akaike values here. This is the threshold values of the stream flows with the equations, and you can see here that if the stream flow water levels surpass the threshold value, it increases the runoff probability in the basin, and the opposite, if the stream flow water level is below this threshold value, the drought happens. So this is our results with GP-RCH combination, and these are the evaluation metrics that we used for GP-RCH models, and these are the scatter plots for our stations. This is our GP CETAR combination model, which we found out that these combination are very good and have good accuracy. These are the scatter plots of them. And in the second study, we try to use the optimally pruned learning machine and chi-square automatic interaction detector models that are both supervised learning machines. And after that, we combine them with RCH models. As you know, the shade can be used for prediction as well. This is another study that used two main and important rivers from western part of the Urmia Lake, and from with the over 31 years of the data, and you can see the selected stations, hydrometric stations here, and in here you can see the training and validation in two stations. Geographical properties of monthly stream flow and statistical properties of monthly stream flow can be shown. And this is our flowcharts that we used the stream flow data collection. Then we use the application of ACF and PICF, and then we use data preparation techniques, then training the data and using the hybrid DDM models, and finally we combine them with RCH models to find out that if the models are have the accuracy or not. These are the autocorrelation and partial autocorrelation of the data in both stations. We normalize data, and you can see that the skewness before the normalization are like this, and after normalization with the equations, the skewness were decreased. And you can see here the scatter plots for TAPIC and DZ stations. TAPICs are red color, and the blue colors are for DZ stations in both calibration and validation techniques. These are the performance of the standalone models for the two stations, and this is our RCH model that we try to find the error part using the Gaussian distribution. And finally, we combined these standalone models with the RCH models, and we found out that how much difference they have with the comparing with their observed stream flow here. So these are the results for two stations. We use the evaluation metrics, correlation coefficient, root mean square error, Nash coefficient, mean absolute error, ratio of RMSE, and the standard deviation, scatter plots, time series plots, and Taylor diagrams as well. So you can see here the results of the combined RCH, OPLM, and RCH shade models for both stations of this agentic and for calibration and validation stages. These are the Taylor diagrams that you can see here. This is our optimum value, and which of these models are closer to this optimum value. We found out that this is our better model in comparison to other models. So as a conclusion, the concept of nonlinearity, parsimonious, and complexity of the stream flow data we considered here and defining to find out the superior model. So this is as I try to read the literature review, there is a little attention in utilizing both deterministic DTMs, data-driven models, and stochastic time series for forecasting hydrological parameter, especially stream flow. And in these two studies, the predictability of newly hybrid DTMs from monthly stream flow for 4 stations were assessed, and the best model were selected. And for ongoing and future research, I can suggest for you that you can use another variance statistics of observed stream flow data, or considering another statistics like mean and cortices for the future studies, or using another bilinear models on another nonlinear models. And we can use generalized autoregressive condition viscosity models and Harsh models. And after that, besides that, we can use data preprocessing techniques for omitting the noises of the data. This is another important issue for the future studies we can do. And some of the priority solutions for Urmia Lake restoration, some of them are in the process, and some of them we should consider more, such as reopening the streams entering the lake and wetlands to facilitate the transfer of water into lake, preventing the unauthorized use of surface waters, removing dikes located in river entries to the lake, transferring treatment plant wastewaters to the lake, organizing the catchment wells, and installing smart gauges, taking legal action regarding unlicensed well and illegal agricultural development. You know, we have such illegal agricultural development alongside our important dams in Urmia. So in the committee, the Urmia Lake Committee, we try to find out this illegal agricultural development and taking the legal actions regarding them. Okay, thank you for your attention. These are my contact information. I'm really I would really happy if I can have a collaboration, have contact with you, and this is my Twitter handle, and this is the link for all of my accounts, such as Google Scholar, ResearchGate, LinkedIn, and etc. And thank you for giving me this privilege. Thank you, Mario. Thank you, Jessica. And I'm ready for your questions. Thank you.
Thank you very much, Nazreen, for what such an interesting talk. Where's my applause? Here it is. We have now some times for questions. So does anyone have a question? Can unmute yourself and just ask Nazreen about it. I have a question, so to start with. So what do you think, Nasrin, will be the role of machine learning in supporting hydrological modeling? Like it's clear that it's a very complex procedure. What do you think is the role that machine learning will have in the future to support different institutions in this?
We at first step we should have good and sufficient data. Here for finding a good data, this is our very I don't know. We can't find a very good data here. So first of all, we should have a good data. So if we have good historical data, long-term historical data, we can use machine learning, because the machine learning is now doing everything. So predicting it has a very good rule. It has a good estimation. So if we have the good data for training the machine very well, it may help. It may help us. I think very much.
Thank you, Nasrin. Any other question? You can type it in the chat too, or just unmute yourself and ask Nasrin. All right. So let's just thank again Nasrin for her wonderful talk and very interesting. So I keep losing my reactions. I don't know what is happening. My computer is really early for my computer too. Anyway, this brings us to the end of this short conference session. Well, almost the end. We have now some time for some networking. So when you registered for this event, you were asked if you wanted to talk to one of the speakers. So you were assigned to a breakout room beforehand. So Maria is going to help us now to open those breakout rooms. You will see a little window popping up and you can accept it. That will bring you to a small room to one of the speakers. So feel free to just introduce yourself, maybe have some networking time, ask more questions, and then we'll be back here in the main room to close the whole session. Thank you very much. We'll see you there.